Right, today in class we learned about complex numbers. We did a little practice with graphing, adding and subtracting them, multiplying and solving. We completed this page 1, and then homework was to do the other 2 pages in the packet. So in case you were absent today, here's what you missed. First, we're going to look at this general idea of just graphing the function of x squared plus 1. Let's go back to our graphing skills. Go ahead and draw in some lines for yourself, like 1, 2, 3, 4, 5. Okay, and so if I've got the graph here of x squared plus 1, I'm thinking to myself, this is like the parent graph. Parent graph is just x squared, but it's plus 1. So it's going to take my parent graph and it's going to shift it up 1 from its original. So normally I would have started at the origin right here. I'm going to shift up 1 and put a dot. From there, it's just growing the normal growth of a parent graph. So we know it goes out 1, up 1. Remember how to do this? Out 1, up 1 in both directions. And then it goes out 2 from that vertex, up 4. And then we connect it, and there's our parabola. Okay, so notice that this is a graph that does not touch the x-axis. So we realize that there are no x-intercepts of this graph. It never touches. Remember that x-intercepts are called real zeros. They're real numbers usually. But however, these are non-real zeros. So we've got to now have a way of representing what do we call those zeros that don't touch an x-axis. So now we're going to go look at the algebra of this. We just looked at the graph of it. We've got this idea started. Let's go look at the algebra of it. And we watched a short video in class on how mathematicians were looking for a way to solve a nice simple equation like this. But hundreds of years ago, when they got to this point, they were like, oh no, we can't take the square root of a negative. What do we do? So originally they were thinking, well, there's no solution to that. But wait, we need a way of representing this function, this nice simple quadratic. So they came up with this idea that by definition, the square root of negative 1 would be represented by this imaginary unit I. So by definition, the square root of negative 1 is defined as I, the imaginary unit. Leave it to mathematicians who can't find an answer, so they make up one, okay? So I equals the square root of negative 1. That's our new definition, and therefore I squared would just equal negative 1. We're going to use these definitions in the following examples. So simplify each expression. Remember that the rules of radicals are only true for real numbers. All right, so negative 9 could be broken down into negative 1 times negative 9. Times 9. And so what is the square root of negative 1 by definition? We now know that that's an I, and the square root of 9 is just 3. So for this example, we would see that our simplified radical is just plus or minus 3i. The next one, we break it down into negative 1 times 6. But 6 is not a perfect square. 6 does not have any perfect squares embedded in there. So sometimes just an I can come out and the root 6 would stay inside. Final simplified answer of this one is I plus or minus I root 6. On the next one, there's a factor of 2 out front. We still simplify this radical. Square root of negative 1 would be I. Square root of 25 would be 5. Don't forget about that factor of 2 in front. 2 times the 5i result would just give us a simplified answer of 10i. Next one is just a quick reminder that anything in two separate houses, in two separate radicals, can be brought under the same radical, the same house. And when I have the square root of a pair of numbers, we know that essentially that means I could just take a -4 out. So that's just a quick reminder. Let's see if you understand that quick reminder. Can you do this one yourself right now? Okay, what'd you get? If you got -3, awesome. All right, -121 and -81. There's a minus in between these two things for what's going on here. They're being subtracted. Let's see what we get. The first one, an I can come out, and square root of 121 is just 11. Next is square root of -81. Breaking that down, a 9 can come out, an I can come out. Now what's happening right here with these? It's being subtracted. So 11 minus 9i, final result is just 2i. How'd you do? Next one becomes -7i squared. It's kind of like we're treating the I as a variable, like an x times an x. Now we know by definition that I squared is equal to -1. So we plug in that new rule, -7 times -1, just +7. How'd you do? Next one is 2i to the third. It's like saying 2i times 2i times 2i. Well, 2 times 2 times 2, that's 8. I times I is I squared. Can't I rewrite that I as a -1? Final answer, -8i. Last but not least, let's distribute this 2i. Gives us 2i squared plus 16i squared. I have a total of 2 plus 16i squareds. But I know that this new rule tells me that I squared can be rewritten as a -1. So my final answer is just -18. All right. The product of imaginary numbers is real. Adding complex numbers, we're going to get real parts, and we're going to be adding imaginary parts. So the format is written as a plus bi. This is the standard form of a complex number. In a plus bi format, we realize that at the front is the real part, and at the back is the imaginary part. Let's go see a few examples and see how we're going to write these answers. So first, we're going to rewrite this with no parentheses so that we can combine like terms. We're just adding, so we're just writing out all these terms. We see that we've got two real parts. We've got a 2 and a -8. That gives us -6. And then we've got imaginary parts of 3i minus 2i. That just gives us 3 minus 2 is 1i. So my final answer has a real and an imaginary part. That's my A plus BI format. Let's rewrite the next one with no parentheses. Remember that when there's a negative or subtraction happening, that's going to change the signs here in the back. It's almost like a -1 is distributing. We see that this has both real and imaginary parts that need to be combined. 2 minus 4 gives us negative 2. Negative 6 minus 3i is negative 9i. My A plus BI format answer is negative 2 minus 9i. Now, what are these called? These are called complex numbers, made up of both real and imaginary parts. All right, last one. We remember multiplying binomials from a couple chapters ago. So first times first, outer times outer, inner times inner, last times last. Now this step a lot of you can do in your head. I just really wanted to show you where everything comes from. So we get 2 minus 8i plus 3i minus 12i squared. Notice that the middle term is like terms and can be combined. And then notice that I squared could be rewritten as negative 1. So 2 minus 5i plus 12, final answer 14 minus 5i, because this 2 and 12 could be combined, and now it's written in your A plus BI format. Here comes your last one.
Get back!